And from there, we started to look at what will happen to the infinite wire or semi-infinite wire. And we also looked at connection of two, finite wires. And even I showed you some more examples from the book where, you are connecting the wire in the form of a triangle. So how to get the magnetic field for this. So you can go through this example. This one is another example. This one is another example where these are the two semi-infinite wires. Okay. And then we started with our Ampere's law, where we looked at the Ampere's law. We have applied Ampere's law for an infinite current wire. We applied Ampere's law for an infinite sheet. And then we were here. So where we were trying to apply Ampere's law for a wire of a non-negligible thickness. So if you remember, we had a wire. So this was a wire, and this wire was carrying current I in the up direction along the Z direction, and it is non-negligible thickness. It has a radius of A. So today we are going to look at a few more examples on Ampere's law, and then, very commonly used inductors. If you remember, we use very commonly used inductors called toroid and solenoids. We are going to look at that, and then the magnetic flux density. Okay, so let's continue with our wire. So this is our wire, and this wire is of infinite length. And now I need to find what is the magnetic field which is generated by this wire. It's a straight wire carrying current I. So for this, let us apply Ampere's law. So what we are doing here, we are applying Ampere's law. So first, if you see here, how do we apply Ampere's law? As I told you, you have to again create your own hypothetical Ampere's path, a closed loop, and then you have to apply Ampere's law there. So here, if I see the top view, so if I see from here, top view, this is the one. So this is my wire, and this is the thickness of my wire A. And now I need to apply Ampere's law. Now, if you see here, we have two regions. So first region is this region, where this is your conductor. Remember, this is your conductor. So this is the region. Now we will see that whether magnetic field can exist inside this conductor or not, because it's of non-negligible thickness. So therefore, now what we are doing is I am now making a hypothetical Ampere's loop inside this. See, inside this. And this is the arrow. And this arrow is decided, the direction is decided according to the direction of the current. Okay, so right hand rule. So my fingers will, my four fingers will give me the direction of my loop, where thumb will give me the direction of the current. So if my direction of the current is up, which is along the Z axis, then the curving of the fingers will be in the anti-clockwise direction. So this is my Amperean loop. So this is the first region. Now the second region will be the region outside this region, the region which is outside the wire. Now, will there be any magnetic field outside this wire? Let's see. And for this, we will have another Amperean loop, which is this one. And I place this Amperean loop in the region of our interest. And this is again the direction. So first, let's go inside this. So first, let's apply it for the red one. So this is for the red one. So closed line integral h bar dot dl bar is equal to the current enclosed, which is our Ampere's law. So now I'm applying Ampere's law. So here h closed line integral h bar dot dl is equal to, now how can I find current enclosed here? Because this current I is carried by this complete cross-sectional thickness, right? The current I is carried by this complete cross-sectional thickness. This complete cross-section is carrying the current I. Now we only need the current which is carried in this region. And this region has a radius of rho. We want only the current carried in this region because this circle is my ampere in loop, which is of radius rho. See, so this is the ampere in loop of radius rho. So I only want the part of the current which is in this region. So how can I find? I can find by using the ratios. So in I, you have which cross-sectional area carries the complete current I? The area of pi a square, right? Because this whole thickness of the wire carries the current I. So the current I is carried in this whole cross-sectional area. Now, can I know that what will be the current carried by this pi a square, which is a partial quantity of this complete cross-sectional area? Yes. So what will be this? This is equal to I times pi rho square over pi a square. So this will be the fraction of the current which is carried by this area, cross-sectional area, which is enclosed in our ampere in loop. So that's how we got this. Clear? Any questions? So shall we move forward? Okay. So then pi and pi cancels. So closed line integral h bar dot dl bar is I times rho square over a square. Now this dot product is converted into just mere multiplication. Why mere multiplication? Again, this is from our experience. So what is our experience here? From our experience. So what will be your magnetic field will be here? So again, if you apply your right hand rule by placing your thumb here, and then we will see that this curving of my fingers is giving me the direction of the magnetic field. So my H will be equal to H of phi a phi, right? Because this is my cylindrical coordinates. So this is the direction of my field. This is phi direction. So this is coming from my experience by applying the right hand rule. And since my magnetic field is moving in this direction, so that's why it is H phi a phi. Now, if you come here, so let me erase this. Yeah, if you come here, so what we have just now seen, we have just now seen that my DL is in this direction, right? And from my experience, my magnetic field is also in this direction. So my magnetic field is also in this direction. This is my H phi a phi. So they are parallel. That's why the dot product is gone and you have just mere multiplication. Now the magnetic field H is taken outside, and what is the closed line integral of dl? The closed line integral of dl is nothing but the length of this ampere in loop, and the length of this ampere in loop is, it's a circle, so the circumference of the circle is 2 pi rho. So H times 2 pi rho is equal to I over rho square plus rho square over a square. And therefore, what we get? we get, so I have to erase this. So what we get H as I times rho square over A square. H times 2 pi rho, sorry, H times 2 pi rho is equal to I times rho square over A square. Or if you see here, my H is nothing but, or I can say this is H or H phi. You can put it anything. So H or H phi. This is equal to I rho over 2 pi A square, or H phi is I rho over 2 pi A square times A phi. So this is my H phi. And this is valid in this region. Remember, because we have applied our Ampere's law in this region. Wow. So from this region, we are seeing that the magnetic field is non-zero. So what does this mean? It means that inside your conductor, which is carrying current I, and if this conductor is of non-negligible thickness, then the magnetic field exists inside this conductor. The magnetic field exists inside this conductor. If you remember, for the electrostatics field, we have seen that for an electrostatic field, if in an equilibrium, the electric field cannot exist there. But here, if your conductor is carrying current, so magnetic field can exist here. Okay, so this is inside the wire. Now, how about outside the wire? So for outside the wire, we have made another Ampere in loop. See, this is the another Ampere in loop. And now we will apply here. And now I'm making this as the radius of my Ampere in loop, rho, and I will apply here. So if I apply here, what I should get here? Yes, can anybody tell me? See, the closed line integral of 2 h bar dot dl bar is equal to current enclosed. So what will be the current enclosed? Yes. Mr. Mishal, can you tell me? So what will be the current enclosed here? What will be the current enclosed in this Ampere in loop? Yes, Mr.
Mishal, sir.
Yes, Mr. Mishal, can you help me? Let's do it together. So what will be the current enclosed in this Ampere in loop? What happened, Mishal?
I don't know.
See, this is your loop. Just look into this loop and find inside this loop, how much is the current? How much is the current enclosed here?
I don't know, actually.
Muhammad Al-Hazmi, can you help?
Yes, hello.
Yes. Can you tell me, Mr. Al-Hazmi, see, this is my loop. So what is the current inside my loop? What happened, Mr. Muhammad Al-Hazmi? This is my loop, and I'm not trying to find what is the current inside my loop. And yes, what I know that in this region, see, in this complete region,
2 by?
No, in this complete region, what is the current carrying in this complete region? I. So the current I is carried in this complete region. And now I want the current enclosed in this red region. So don't you think, Mr. Hazmi and also Mr. Mishal, don't you think that the current enclosed in this red, in this red loop is nothing but it's this complete blue part. Yes, it's the complete blue part, right? Yes, what happened, Mishal?
Yes, I'm
Yes,
here.
right.
Yeah, Mr. Hazmi, this is the complete
Yes.
blue part, right? And what is this complete blue part? Is your current I. So it is this I. In the previous case, it was different. In the previous case, this was the radius A, and my ampere in loop was here, which is this one. So therefore, we were trying to find how much is the current enclosed here. And what we know, we knew that the current in this whole region, this green part, the complete green part, was I. So therefore, in this blue part, it will be the fraction of I. And this is how we found it is I times pi rho square over pi a square. That was the fraction. But here, in this case, it's different. In this case, our ampere in loop is very large and it is enclosing the whole current I. So that's why you have this whole current I. So did you get it, Mishal and Mr. Mohammad Al-Hazmi?
Yes, doctor.
Yes, Mishal. How about others? Did you guys get it? So that's why we write it here, I. And again here outside our magnetic field direction, again with our right hand rule, this is our magnetic field direction. So again, it will be H phi A phi, and my DL will be this one. So both will be parallel. So again, this will be just mere multiplication is equal to the current I. So therefore, my H close line integral DL is equal to I, or my H times, what is the circumference? What is the length of this red loop? What is the length of this red loop? Yes, Mr. Mohammad Al-Hassan, at least you can tell me now. What will be the length of this red loop, or Mr. Mishal? What will be the length of this red loop? See, this radius is rho. So what will be the length of this red loop? It's 2 pi?
2 by B.
No,
Rho.
2 pi rho is equal to I, or H is equal to I over 2 pi rho, or in terms of vectors, H bar is I over 2 pi rho A phi. So this is in the region where your rho is greater than A, that is greater than the radius of your wire. And this is the expression for rho between 0 and A, that is inside the wire. So this is inside the wire, this is outside the wire. So it is inside the wire. If you see, guys, inside the wire, it is proportional to rho. That means it is like linear increase. So the magnitude will increase almost, linearly. And here, 1 over rho. So inside the wire, as you approach near the wire, your magnetic field will increase the magnitude. But as you touch this wire end, and once you go outside the wire, the magnetic field magnitude will increase as 1 over rho. So this is how you can find the magnetic field by applying Ampere's law. Clear? See guys, I'm spending a lot of time on this example because I want you guys to understand it clearly and don't have any doubts, because there are several examples in the book and problems in the homework which uses this concept. So you should be clear with this. So whatever I have explained, this is what we got. And inside the wire, outside the wire. Linear, but once you go outside the wire, it goes as 1 over rho. Got it? And if you recall, this is very similar to our sphere, which is carrying the volumetric sphere, which is carrying a uniform charge density rho v. So here also for this sphere, we saw that inside the sphere, the electric field will exist and it will be almost like this. It will go linearly, and then once you go outside, it goes down. It goes down. This is very similar to this one, this example, which, if I'm not mistaken, we did it in lecture 4. Okay. Now let's move ahead. So this is the so we already saw the Ampere's law. Now we are just rewriting the Ampere's law. So we rewriting the Ampere's law. So this is my Ampere's law is equal to the current enclosed. And this is the general expression of the current. So I is closed surface integral J bar dot ds bar. And by the way, why we were able to, a quick question, why we were able to use these ratios to find current? Can anybody tell me why we used these ratios to directly get this current value, and why we did not use this general expression to find the current? Can anybody tell me? Yes, Mr. Abdul Malik Muhatib. Do you know why?
No, Doctor, I don't know.
No? Mr. Abdullah Ali, do you have any answer?
I'm not sure, Doctor.
Not sure? Okay, Abdul Majid raised hand. Yes, Abdul Majid,
Doctor,
can you tell me?
I think we can generalize the equation if we have different wires, different length, and so.
Say it again, Mr. Abdul Majid.
So we can generalize, I mean, the equation if we have wire of different lengths and so, or different parameters.
You are not exactly, close to what I was looking for. We used directly this way of finding the current inside, and we did not use this expression. The reason is our wire has a uniform cross section. It has a uniform cross section. So this generalized expression, guys, I can use this expression. There is no problem. I can use this expression and I can get this. There is no problem. You can do that. With all due means, you can take and you can find how much current is going out from this surface. This is your ds. You can do that. And you have this current I. So do the surface integration and you will get it. But here we used a shortcut method. So this is, I can say it's a shortcut method. We avoid this integration. Reason why we could do that, because my cross section is uniform. My cross section is uniform. So therefore, I can use this quick way of finding the ratios and getting the current. So which ratios? If the whole current is enclosed in this cross-sectional area, then in a small cross-sectional area or a fraction of a cross-sectional area, how much will be the current enclosed? So this idea can be used when your current is of uniform cross-section. Your wire is of uniform cross-section. Otherwise, no. Otherwise, you have to go and you have to apply this generalized expression and find the current. So I hope it is clear. Yes, Mr. Abdul Malik Moheti and Mr. Abdullah Ali.
It's clear, Doctor.
It's clear? Yeah. So, these things you have to take a note. So where you can use these shortcut methods and where you cannot. Okay. And yes, so now let's go to the differential form. So in the differential form, I'm replacing the integrals. So I'm using Stokes theorem here. So line integral, I'm converting it into the surface integral. So therefore you will have curl of h bar dot ds, and here you have j bar dot ds. So both are in surface integration. So therefore both inside the surface integrations must be equal. Therefore I will get del cross h bar is equal to j bar. This is Ampere's law in differential form. And this is the Ampere's law in integral form. Very similar to how we got for the Gauss's. Now there is one thing which you should note. See here what is happening. Del cross h is no longer j. Del cross h is no longer del cross h is no longer 0. Del cross h is j. If you remember in electrostatics, what we got del cross E is equal to 0. And that's why closed line integral E bar dot dl bar was 0. And therefore we said that the electric field is conservative. But here it's not the case. Del cross H is not equal to 0. So therefore electromagnetic field is non-conservative. The magnetostatic field is non-conservative. Okay, it is non-conservative. So this is, you need to understand this. Now, there are another good example for your coaxial cable, okay, which is the extension of the previous example that we did. But here you have an inner conductor and an outer conductor. Okay, so I want you guys to go and look at this example. So our objective is to find what is the magnetic field here, to find what is the magnetic field in the region between those two conductors, which is our dielectric region, and find the magnetic field of this outer conductor, because here our outer conductor also, we took it as non-negligible thickness. And then outside our coaxial cable. So 1, 2, 3, 4, 4 regions. Again, the cross section is uniform. So therefore you can use the idea of the ratios that we did it in the previous class. And then you can go through this. Okay. Now let's go to this one. So derive an expression of h bar everywhere for a toroid with n turns and carrying current I. So now what is a toroid? Toroid is a special name given to this kind of wire. So it's a wire which is wounded, and it can be wounded on any dielectric material, which is called as core material, or in this case it is free space, and they are put and it is wounded in the form of a circle. So this is called as toroid. And this was very common type of inductor which was used in 80s. Okay, in 80s, there were two very commonly used conductors in our electronic circuits. First is this toroid, another is solenoid. Solenoid is when you wounded and put it in a straight line. Then this is called as solenoid. And this is called as toroid. And you can wrap it with, on a material also. And this material is called as the core material, or it is called as a core. And these are very commonly used in 80s, in 1980s, in our electronic circuits, the inductors, toroid and solenoids. But unfortunately, with the significant advancements and other things, all the inductors are almost obsolete now. So we don't use inductors because we are able to get all our circuits, but working with capacitors. So mostly capacitors has overtaken everything. And the reason is this are of, they take a lot of space, and also they are bulky. So in order to, shrink our electronic circuits, we had to, say, make this obsolete. And the second thing is capacitors, resistors, they can all be embedded in an integrated circuit. That means you can easily make it shrinkable, because you can easily realize it in an integrated circuit in a very, very compact form, not in inductors. So hence the whole electronic circuits the electronic circuits was revolutionized with only these components, and inductors were removed. But still, in our case, these are very good examples to understand our magnetostatic field. So this is your toroid. So in your toroid, so these are your wires, see, and your wires are wounded in this way. So the other end is going like this. Like this. Okay. So if you see from the front, it looks like this, a circle here and exact replica here. And the radius of this is A. So therefore the diameter is 2A. The diameter is 2A. And the distance between this to the center is rho 0. And this is my Z axis. Okay, so it's time, guys. Yeah, I think we should stop here. And we will look at this example in our next class. So first,